In this lesson, we're going to discuss hypothesis testing. Hypothesis testing is a very important part of statistics because it allows us to use samples to make conclusions about populations. Researchers are often interested in answering lots of different questions. Does a new medication lower blood pressure? Does the public prefer a certain color in a new fashion line? Is a new teaching technique better than a traditional one? These types of questions we can analyze using hypothesis testing, a decision-making process for evaluating claims about a population. A hypothesis is a conjecture or an educated guess about a population parameter. We are going to focus on the population parameters of a proportion and a mean. We could look at hypothesis tests for standard deviation and variance, but in our class we will not be doing that. This hypothesis that we make may or may not be true. And that's the idea behind the hypothesis testing, is using statistics to determine the likelihood that the hypothesis is true. We can never be 100% certain, and so we get to adjust our confidence in a way in regards to our hypothesis test. There are two types of hypotheses. The null hypothesis, symbolized by H0 or H0. The null hypothesis states that there's no difference between a parameter and a specific value or between two different parameters. No difference means that they are equal. Our null hypothesis will look something like proportion equals 0.15 for 15%, or the mean equals 70. Or if we're talking about two parameters, that's for chapter 9, we could have one mean equaling another mean, for example, or one proportion equaling another proportion. The big idea for null hypothesis is we always have equality in our statement. So our null hypothesis will always include equals. The alternative hypothesis is symbolized by H1. Sometimes you'll see it as H sub A. In the alternative hypothesis, there is a difference between the parameter and the specific value, or there is a difference between two parameters. And those differences can come in different forms. We could have a proportion not equal to 0.15. We could have the mean greater than 70, for example. Or we could have the alternative of the first mean being less than the second mean. And these are just examples. It depends on our situation, but we could have a not equal to, a greater than, or a less than for any of our hypothesis tests, depending on what our claim is, what the situation is, how our scenario is set up. Both hypotheses are required for every hypothesis test. We have to be able to identify the null hypothesis and the alternative hypothesis, and we have to choose one of them to be the claim, and we'll talk about that in just a minute. Methods that are used to test hypotheses, there are 3 of them. 2 of them are directly related to each other, the traditional method and the p-value method. In the traditional method, we're comparing the positions of values. So similarly to what we were doing when we had that normal distribution and we would put some value on our normal distribution in relation to the mean, we're going to have another value that will determine our conclusion for our hypothesis test, depending on where the two values sit in relation to each other. We'll have a test statistic and we'll have a critical value. And so here's one example where the test statistic given by x1 and the critical value given by CV. We could have a test statistic that sits on the other side of the critical value. And that's really the situation. Where does the test statistic sit in relationship to the critical value? And again, we'll talk more about this a little bit later, but just trying to get a little heads up on where we're headed. The p-value method compares probabilities. So we'll still get these two values. Well, we'll get the test statistic value, the x, and then we'll find the probability associated with that x and compare it to our significance level, which will be something that we decide at the beginning of the test, kind of like our confidence in the test in a way. And then the confidence interval method deals with creating a confidence interval and then determine if the value that we have is inside that interval or not. We're not going to be looking at number 3 for our class, this confidence interval method. Just know that it exists and that some researchers could use the confidence interval method to conduct a hypothesis test. We just don't often do it. Technology can give us answers, numerical answers, but for hypothesis tests, we must go beyond just the answer and just the simple conclusion. We need to focus on how the hypothesis test works, learn the terminology, and interpret our result. That's what we're really going to focus on with the hypothesis tests. A researcher conducting a study is generally looking for evidence to support a claim. He usually states a claim as the alternative hypothesis or the research hypothesis, but it doesn't have to be the research or the alternative hypothesis. Remember, the alternative hypothesis is H1. But we could have a claim that is the null. If we want evidence to support a claim, then we need to have that claim be the alternative hypothesis, because statistical evidence can only support a claim if it is the alternative hypothesis. Looking back to the different hypotheses that we had, notice that for the null hypothesis, we're looking at one single value of equality, p equals 0.15. If we're looking at the alternative that I just made up on the side, p is not equal to 0.15. We have so many more possibilities for the alternative hypothesis to be in comparison to the null hypothesis. And that's what makes the statistical support for the alternative hypothesis. Similarly, in the other pairs of hypotheses that we have, mu is equal to 70 or mu is greater than 70. Mu is greater than 70. I have infinitely many more choices for mu. Otherwise, I'm looking at a single value in that null hypothesis. So the statistical evidence can only support the claim if it is the alternative hypothesis. We can use statistical evidence to reject the claim if the claim is the null. This is going to make a difference when we state our conclusions, whether the claim is the alternative or the null. Here's an example from a study done. In January 2020, an article, which I'll give you the link to, has a claim: more than a third of consumers prefer drone delivery. A business firm, Clutch, surveyed 528 shoppers, and from that survey, they found that 36% say they would be more likely to purchase an item if it were delivered by drone. Here's an example of a hypothesis. Because we're coming at it from a sample, we got this information from a sample. This statement, more than a third of consumers prefer drone delivery, notice that this is a generic statement about the entire population. This is a claim about the whole population. The part about surveying 528 shoppers and determining 36% is part of the statistical evidence to support that claim. We could write this statement as a hypothesis: more than a third of consumers, 1/3 is a proportion apart 1/3 of the whole. So we have a claim about a proportion, and it's somehow related to 1/3. More than tells me that my proportion should be greater than 1/3. And since my proportion is a greater than and not equal to, this is an alternative hypothesis that we then would call our claim. If I want to find the null hypothesis that goes with this alternative, the null hypothesis is exactly the same symbols, except the inequality should be in equals. P equals 1/3, and then the alternative P greater than 1/3. So these would be our hypotheses for this particular hypothesis test, if we were running it on our own. But let's say we decided to collect our own data. Instead of using their data, the 528 shoppers that they collected, let's suppose we went out, collected our data in an appropriately randomly selected way that we've already discussed for our sampling methods. And suppose for our survey, we found only 32% were comfortable with drone delivery. The big picture is, does this 32% result that we got, is it enough to say that their claim of 36 is okay? Or does it contradict? Notice that 32% is not greater than 1/3, which was their original claim. But of course, this is just one example of many different scenarios that we could look at. And this is the case with any experiment or survey that we do in statistics. We want to get an idea of the actual population parameter, whether it be mean or proportion, particularly for our class, what that actual population proportion is. But we cannot survey everyone, or we cannot experiment on everyone. It's not feasible, so we take samples. It is not necessarily the case that the bigger the sample, the better the results. We do need to be careful with how we're choosing the sample. And so that is something to look at when you're looking at different statistical reports to see if they indicate how their sample was collected. You want to make sure it's one of the approved probability sampling techniques that we've already discussed, like simple random sample, systematic sampling, cluster sampling, or stratified sampling. There could be some combinations of those in different ways. A multi-tiered sampling with those techniques could work and be okay. We just want to make sure that the sampling technique is not convenience or volunteer. We know that those are considered bad sampling techniques and can give us biased samples. So let's talk about a hypothesis test. Some examples for us to try out on our own. We're going to set up the test. The first part is identifying the null and the alternative hypotheses. Once you have your scenario in place, you need your hypotheses. So we're going to express the null and alternative hypotheses in symbolic form, like we did above, and then also identify which hypothesis is the claim. There's always a claim. Only one of them can be the claim. And so we will determine that from how our scenarios are written. Look at A. A city planner might want to find out if the claim that the average wait at an intersection for his city is greater than 4 minutes is true. There are some pretty big keywords here. Average is a big one. That means we're looking at a population mean. Another helpful word, greater than. And this is his claim. So let's write this part out. Average wait is greater than 4 minutes, and this is his claim. Because I have greater than in this statement, this is my alternative hypothesis. To get the null hypothesis, the mean stays the same and the 4 stays the same, but the inequality in the middle is an equal sign. And so again, those symbols should be identical. Whatever numbers are on the right should be identical. It's the symbol in the middle, the relationship, that's different. Looking at part B, a biologist might want to find out if the claim that the proportion of green peas in a harvest is 75% is true. We have proportion, so I know I'm looking at a P. Proportion of green peas in a harvest is 75%. Is equals. And this is my claim because it says it is my claim. So I can write that down. Claim. Since I have an equal sign here, this is my null hypothesis. The alternative hypothesis that would go with this, P and 0.75, stay the same. And I have nothing in the problem that tells me if P should be greater than 0.75 or less than 0.75. So P is going to be not equal to 0.75. We're only given that it's equal to 0.75, so the opposite of that would be not equal to. And then part C, a mechanical engineer might want to find out if the claim that the average speed for certain wind turbines is less than 10 miles per hour is true. We have average speed, so this is another claim on the mean, less than 10 miles per hour. And again, I know this is my claim because it says it is. I have an inequality, so this is my alternative hypothesis. To get the corresponding null hypothesis, mean and 10 stay the same. Null hypothesis is always equal to. Your textbook uses less than or equal to and greater than or equal to for that null hypothesis. And that's okay. We have different textbooks that use the equal to signs for the null hypothesis, even if it's less than or equal to or greater than or equal to. If we have these symbols in our null, then the corresponding symbols in our alternative should be not equal to, greater than because it's opposite less than or equal to, and less than because it's opposite of greater than or equal to. I tend to write only equality in my null hypothesis. That's my preference, and that's how I learned it, and that's how a lot of other textbooks use it that I've taught from. So I like just keeping it as equal to, but know that you could have the situations of less than or equal to or greater than or equal to pop up, and those are still considered null hypotheses because they contain equality. They have the equal sign in there. In writing hypotheses, as you've seen, we're going to write the claim to be tested in mathematically symbolic form. We know it was the claim because we wrote it right after, and then we decided was it the null or the alternative based on that inequality or equals in the middle. And then we were able to write the other corresponding hypothesis by determining the statement that must be true if our claim is false. What's the opposite of our claim? And here we have for the null hypothesis equal sign or greater than or equal to or less than or equal to. Those are okay as well. And then for our alternative hypothesis not containing equality, we have greater than, less than, or not equal to. In the next part of our lesson, we'll talk about the significance level, the different types of errors we could have, and then more about our hypothesis test.